எடுத்துக்கோங்க. I think there is only 3 members present here. I don't know what about the rest of us, rest of the members. 5, 3, 7. Okay. Good morning. Is my voice audible? Good morning, guys. Okay. So I don't know how long we have to wait. So shall we move to today's portions? The remaining in alkali metals and the rest of the thing in alkaline earth metals. So I think you're making a message to me. Good morning, ma'am. Okay. Suprajit Sahu, good morning. Shreyan Shetia. Good morning, ma'am. You're audible. Fine. Okay. So have you, yeah, another one more connected. Kanish. Good morning, Kanish. So still there is some girls, I think they need to attend it. Shairaja, what about them? Okay, fine. So have you gone through the portions which I have taught yesterday? Well, you're able to get my point. What are all the things I taught yesterday? Is there any doubt? I have also given my personal number also. If there is any doubt, please make sure to ask it. Okay. Respond me. I think I can't connect it. There is only 5. Well, what about the rest of the persons? So shall we move to today's questions? Is it okay? Or well, I don't know how you peoples will be going. I don't know. Well, once all the members were present, then only you will start the class, or it's okay to start now. We can start now. Okay, sure. So I'll go. That's it. Okay. So this is what the thing I have taught till yesterday. So actually, I'll go for a quick recap. So what are all the things I have taught yesterday? So yesterday I have been discussing about the alkali metals. So initially I gave the introduction about the electronic configuration and the trends, which includes atomic size, ionization enthalpy, density, and we have seen about the chemical properties where how the reactivity with oxygen, hydrogen, nitrogen, halogens, etc. And also in the physical properties, we see the trends, which is like how the stability of the carbonates or the oxacids and also with the sulfates and everything we have seen yesterday. And finally, we have gone through the preparations and anomalous behavior and the diagonal relationship. So today in preparations, there is another 2 compounds were remaining. So first one is sodium hydroxide. Okay. See, yesterday I have taught about first one is sodium carbonate. Okay. That is a washing soda. That is Na2CO3.10H2O. Okay. Sodium carbonate decahydrate. And second one, I have taught about sodium chloride, and now I am be teaching caustic soda. So how this caustic soda is obtained in the sense, initially what happened, you have to place a beaker. Sorry, it's not a beaker, it's like an in electrochemistry you will know there is one kind of a vessel, okay, where here you have to drop your brine solution. Okay, so brine solution is nothing but NaCl, that is sodium chloride solution will be there in it. So there you have to place the mercury as the cathode and the carbon as the anode. Okay, so cathode which is negatively charged and anode is positively charged. If it is negatively charged, in the sense, in the solution the sodium will be present as Na plus and Cl minus. So being the cathode negatively charged, all the positive ions will flow through this cathode, and anode which is positively charged, what happens? All the Cl will move towards this anode. So what happens? Cathode is a place where the reduction takes place, right? So reduction in the sense gain of electrons. So the sodium, what happens? It will gain the electrons. That is what the reaction which is represented here. The Na, that is the sodium ion, will take the electron from the mercury and it forms the sodium amalgam. And in anode, the oxidation takes place where the loss of electron happens. So this chlorine, what happens? It will release as its electron. So what happens after gaining? I'll write here. So what happened once this sodium amalgam, okay, so it will react with water, and finally what happens here, your sodium hydroxide and your hydrogen gas. So to balance, it will be like this. So 2 sodium hydroxide and your hydrogen gas will be released, and finally your mercury will be also getting separated. Okay, this is for the final reaction, and from this reaction only sodium hydroxide is obtained. So this sodium hydroxide is obtained by an electrochemical method where you will be placing the mercury as a cathode and the carbon as the anode. Okay, so cathode in the sense what happens, being negatively charged, the positive ions flows towards it, and the anode which is positively charged, where all the negative ions flows towards it. And in cathode the reduction takes place, anode oxidation takes place. That's why what happens, there will be a gain of electrons. In anode there will be a loss of electrons. On gaining the electrons, this sodium will be present as a sodium amalgam. Again you're treating it with water. So what happens here, our sodium will react with water and it forms sodium hydroxide, and the hydrogen gas will be released. Finally this mercury is also getting separated. So clear with this concept? Clear guys? Wait, I'll go and check in the chat. Okay, everyone is present. Yes, ma'am. From Ashwath to everyone, ma'am. Hasini will not attend the class today. Okay. So I have parallelly 2 screens. No, if I want to see your chat, I have to come through the another screen. If it is possible, please say yes or no. Okay. So I need to open another window. I need to check whether you guys understood or not. So if possible, please answer and say yes, ma'am, or no, ma'am. Okay. Yes. And now coming to the next preparation. Okay. Huh. This sodium hydroxide, what happens? It's a translucent solid in the sense it will be transparent solid. In your lab, you know the sodium hydroxide will be present in the form of pellets. Pellets in the sense it will be round. Actually, when it is kept in the air, what happens? Initially, it will be melted. Okay. So what happened? The reactivity with air, I mean in presence of carbon dioxide or air, whatever it might be, it easily will be getting melted. So it melts at 591 Kelvin. It will easily soluble in water, gives a strong alkaline solution. So have you ever dropped the sodium hydroxide crystal in water? Have you done this experiment in your lab? If you keep on stirring, what happens? The beaker will be very much hot. It is not lukewarm. It will be like a piping hot. So what happens? It is an exothermic reaction where more amount of heat will be getting released. Okay. So it forms a strong alkaline solution. And finally, as I already said, this caustic soda, that is the sodium hydroxide, when it is treated with CO2, what happens? It forms sodium carbonate. That is, if you're just keeping the sodium hydroxide, when it is present, it will react with the atmosphere carbon dioxide. Okay, and easily it forms a sodium carbonate. Clear? So this is the applications. Okay, that is the physical properties of sodium hydroxide. So here the sodium hydroxide is getting ended, and the next one we are going to see about the uses. Actually, this sodium hydroxide, it is actually mainly used in, first one is like, it is maximum used as a bleaching agents. Okay, so if it is soap or paper or artificial silk, wherever it might be, it is used as a bleaching agent. In petroleum refining, what is meant by petroleum refining? Actually, petroleum refining is nothing but a crude oil. No, initially the petrol or refine, it is not obtained as like a purest form. Initially it will be present as a crude oil. So from that it can be converted into petrol, kerosene, or liquefied gas, whatever it might be. So for that process, this sodium hydroxide is used. So purification of bauxite. Bauxite, I think you have heard this word in your metallurgy. It will be like Al2O3.H2O. It's a principal ore of aluminium. Okay. So from this ore only the aluminium metal is getting extracted. Okay, so aluminium as such it is not present as aluminium. So aluminium is present in an bauxite ore. Okay, so from this there will be many process like froth flotation process, hydraulic washing, gravity separation, many process will be there. So finally in the purification, this sodium hydroxide can be used as a reducing agent in the purification of the aluminium. Okay, yes. Next one is in textile industries as a bleaching reagent, and also in preparation of pure oils and fats. Actually, there is known as saturated fats and oil. Actually, initially, all our cooking oils will be like, many impurities will be present there. So this sodium hydroxide is used as a bleaching oil there, where you can finally make it as a refined oil. Refined oil in the sense it's completely filtered, and it is like a purest form of the oils. That's why it's just said as refined oil. Even it will take the good fats also. Okay, so the preparation of pure fats and oils, finally in laboratory reagent also it is used. So next one is, these are all uses, you can also go through your own. Sodium hydrogen carbonate. So this sodium hydrogen carbonate is, in the preparation of cakes, they'll add many ingredients like cocoa powder, all-purpose flour and everything. So in that they will add this baking soda. Okay, why they are adding this baking soda in the preparation of cake? Any answer? So again, I need to check there. Well, you have. Do you know why this sodium bicarbonate or baking soda is used in the preparation of cake?
Ma'am, Subhrajit says evaluation of CO2.
So what evolution of CO2 means? How evolution of CO2 will take place? Actually, what happens there in the sense, when you're just adding, initially you will mix all the ingredients. Okay, so when you're adding this sodium bicarbonate or baking soda into that cake process, what happens after heating? What happened? It will be getting raised. Okay, it will be getting doubled. So what happens there, and you can find there will be a small amount of holes will be there, that is known as air bubbles. So where the CO2 is getting released there. Okay, so that is why the sodium or this baking soda is added as a main ingredient in making the cake process. Not only in cake, in everywhere they'll use the baking soda. Okay, so actually it is also used in a cleansing reagent also. So that is what they have been said here. The preparation is very simple. You have to take the sodium carbonate, you have to mix it with water with the CO2, carbon dioxide gas. Finally what happens, the sodium bicarbonate will be obtained. Okay, in hospital orientedly, it is used as an antiseptic for skin infections, where wait a minute. Okay, wait a minute. See, yes. So next, it is also used in a fire extinguishers. In fire extinguishers, the white color gas will be released, where the baking soda is also one of the component in it. Okay, so here comes the ends of this alkali metals. So we have discussed all the compounds according to your NCERT syllabus. Do you have any doubt regarding this thing? Evolution of CO2 leads to rise in cake. Suprajit Sahu. Guys, can you please answer my question? Is there any doubt till this alkali metals?
No, ma'am.
No. Okay. Everyone is like clear and confident. Whatever part from wherever, if I'm arising the question, you'll able to answer it. Seriously? I'm checking the chats also simultaneously. Everyone got it, every point. So have you gone through what are all the things I have taken yesterday? There is no doubt. Is it able to understand every concepts? The stability of carbonates, the solubility of carbonates, the standard reduction potentials, and what happens, why it's give the high negative values, and the trends, everything you got it?
Ma'am, if it's possible, could you send the PPT?
Yeah, I'll send the PPT, no issues.
Okay.
I'll send the PPT. If there is any doubt, please ask me here. Or if you are quite hesitant, please connect me through my WhatsApp number. I'm there to answer and clear your doubts. Okay.
Okay, ma'am.
Yes. Shall we move to the next thing? That is alkaline earth metals. So far, we have seen about the alkali metals. Now we are getting through the alkaline earth metals. Why it is known as alkaline earth metals in the sense? Because all these metals are naturally obtained from the earth crust. Okay, there you can see the sodium, potassium, everything, some from the ocean, some from the sea, some from the earth crust, but all these elements it will be obtained naturally from the earth crust. So that is why it is known as alkaline earth metals. This is the first slide, and next one regarding this is, as I already discussed, for alkali metals it will be having NS1. Okay, this is what the electronic configuration. For alkali earth metals, the electronic configuration will be of Ns2, because in valence shell, there will be 2 electrons present. Okay, so beryllium, if you're just taking the beryllium, the atomic number of beryllium will be 1s2, 2s2. Okay, so for magnesium, I think you can see here itself. For magnesium, the electronic configuration will be 1s2, 2s2, 2p6, 3s2. Okay, so you can see this 2s2, 3s2, 4s2, 5s2, and 6s2. All the valence electrons has only 2 electrons in its outermost shell. So that's why the general electronic configuration of this alkaline earth metals is Ns2. Okay, clear? So next one, we can get into the next slide. As already discussed, this atomic and ionic radii, what happens from top to bottom, it will be showing only the increasing trend. Okay, because as the number of shells is getting increased, the screening and shielding effect also getting increased. See, the thing is actually what you studied in the periodic table, no? So that the trends will be applied for S block, P block. Everywhere this atomic size, ionization enthalpy, electronegativity, density, melting point and boiling point will be similar. But only you have to concentrate when there is an exceptions is there. Why the exceptions is arising, you have to know the reason. But here there is no exceptions. In atomic and ionic radii, down the group, what happens? It will be beryllium greater than magnesium, greater than calcium, greater than strontium, greater than barium. So this is what the trend will be followed. So top to bottom, this will follow only the increasing trend. Next one. Yes. To come to this table. Okay, so here, concentrate. You just don't atomic number, fine. Atomic mass, it's showing an increasing trend. Electronic configuration, already you know it. Ionization enthalpy, what happens for, wait a minute. So I think I am, okay, it's coming here, no issues. So ionization enthalpy, what happens for beryllium, it will be more, because what happens in beryllium, the size is very, very, very small. So to extract the valence electron for that shell, more energy should be observed. So that's why it's showing 899. So rest of the things is showing the decreasing trend. Down the group, the low ionization enthalpy will be followed. See, don't worry about this radium. Okay, so we can't easily take the radium and we can't easily undergo it in a chemical reaction because it is highly radioactive. So always compare from this to this, that is fair enough. Okay, because this kind of like radioactive elements, they'll be treated under certain conditions. Okay, so you don't worry about this radium, just compare this 5 elements. And next one is, have you seen they have compared the first and second ionization enthalpy? I'll come to that thing in the next slide. The hydration enthalpy also will be there in next slide. So here the metallic radius, what happens, it shows an increasing trend. Okay, so down the group the metallic nature will be very more due to the highly electropositive nature. Okay, and ionic radius also follows an increasing trend. See, have you seen there is an trend of the melting point? Yes, the first element shows the high melting point, right? So here it is 1560. Fine. So there is no systematic trend for the next 4 elements. Why? Actually, in alkali metals, the first elements will show the highest melting point and boiling point, and down the group you can see there will be a kind of decreasing trend. That's why as a whole they will be melting, as the whole they'll be mentioning it as a low melting and boiling point because of the weak metallic bonding, right? But here you can see for melting point of beryllium it is 1560, and for magnesium it's 924, but for calcium, strontium, barium, you can see there is a difference. It should be getting decreased, right? But here there is 3 exceptions. The similar thing also in boiling point. In boiling point you can see, of course this is a small, the beryllium is very small. Its crystal lattice is tightly packed, so it is having 2745. In magnesium you can see it is 1363, but again in calcium again it's getting raised. Okay, for strontium it's 1655, but for barium again it's showing 2078. You can see the trend is not systematic. Why the trend is not systematic? Can you able to get my question?
Is it because the screening effect increases in calcium?
Sorry, screening effect of calcium.
Yes, ma'am, because it increases.
The screening effect increases. Yes, the screening effect increases for, wait. Yes. So you're saying, okay, in boiling point, you're saying the increasing screening effect. Okay. But for barium, okay, see, the melting point and boiling point, as you said, it's close. But the thing is also, see, for all the 3 elements, there is quite low ionization enthalpy is there. Okay. So the high ionization enthalpy will be there for melting, they will be there for beryllium. But from magnesium, calcium, strontium, barium, you know what happens? There will be low melting points. Because of that low melting point, what happens? Sorry, low ionization energy. Yes. Because of that low ionization energy, what happens? The trend is not systematic, and also the lattice arrangement is also not systematic. Okay. Because comparatively, if you're just taking group 1 and group 2 elements, the group 1 elements will be larger in size than group 2 elements. Correct? You can get my point. Group 1 elements will be larger in size. Okay. Do you understand this point? Why I'm saying this thing?
Yes, ma'am.
That's the thing. And also the group 2 will be small in size, and what happens down the group, there will be the low ionization enthalpy follows. You just don't need to worry about this thing. The trend is not systematic here. Okay, that is because of the low ionization enthalpy. That's it. Next one is density. Look at the density. See, beryllium is having 1.84, magnesium is 1.75, the calcium is just having 1.55. The similar thing follows. What happens? The volume showing an increasing pattern. So what happens there? Quite a confusion thing happens. So the density will be in the order of calcium, okay, which is greater than magnesium, and the beryllium will be here, okay, and strontium and barium, okay. So what happens in the sense? the mass and the mass will increase, the volume also will increase in calcium. So that's why what happens, the calcium will be having the less density, so it will come here, and then magnesium, and then beryllium, strontium, and barium. This is what the density trend in alkaline earth metals. So do get I think everyone can able to get this right. Density, melting point, and boiling point clear.
Ma'am,
Yeah.
could you repeat why the melting point of magnesium is lesser than that of calcium?
Due to the low ionization enthalpy, man. Actually, what happens, low ionization enthalpy in the sense, for magnesium, you have to give the high ionization enthalpy to remove the electrons. For calcium, what happens, you have to give the low ionization enthalpy because the shell is getting increased. You can easily remove the electron. So that's why what happens, the magnesium is having the less melting point, the calcium will be having more melting point due to low ionization enthalpy. Wait. This will be discussed in your
Ma'am,
yeah.
then that trend should also follow between magnesium and beryllium, right?
Yeah, you're right. Magnesium and beryllium, right? But here what happens, beryllium, apart from the group 1, apart from, see you, that's why I said the group 1, wait, the group 1 and group 2, if you're just comparing the size, this will be very much small. So if it is very much small in the sense, what happens, there will be the high ionization enthalpy will be there, right?
Yes, ma'am.
So that's why, that's the reason. What's the point is like, you can't understand. Now you got it?
Ma'am, but we are comparing between group 2 elements, right? We are not comparing
Yeah,
between
group 2
group.
elements you are comparing, but I'm just saying to information is this group 2 elements will be of very much smaller in size, right? So if it is very much smaller in size, definitely you need to, give more ionization enthalpy. Down the group, what happens? The ionization enthalpy will be less, right? I'm just only saying about the size.
Yes, ma'am.
Okay, so you don't, I'm comparing this group 1 and group 2 to get the better understanding of the size. Okay, so you just only, you can say, if you're just seeing the group 2, it will be very much smaller in size. Okay, so what happens for beryllium, you have to give the more ionization enthalpy to remove the valence electron. But here in case of calcium, what happens, in calcium, what happens here, you have the low ionization enthalpy, but still what happens in strontium and barium, there will be low ionization enthalpy, but the crystal lattice arrangement, it will be very, very weak. So that's why what happens, it will be like 1062 to 1002. Clear? Only thing is you have to remember, due to the low ionization enthalpy only, this trend is not systematic. Okay, clear with this point?
Okay, ma'am.
Okay, so next one, have everyone got the density point also clear? Yes, come on, answer me. Everyone got this density, melting point, and boiling point clear?
Yes, ma'am.
Drop, okay, drop the message
Yes,
in.
ma'am.
Okay. Yeah, someone is like saying anything? No. Okay, so next one is standard reduction potential. So here in standard reduction potential, it is nothing but the reducing power. Okay, see, you don't need to get into very much detail. Just compare this standard electrode potential is having the negative values. Okay, so what happens? The negative values are getting in this trend. So if I'm comparing this thing with the first element, the first block, the group 1, which is nothing but your alkali metals, there what happens? There will be a high standard electrode values will be there. So wait. Look at here. See, it will be having minus 3.4, minus 2.5, minus 2.9, minus 2.9, minus 2.9. But here, But here, if you're just seeing, for the first element itself, see, it is minus 1.9, which means what? If I'm comparing the group 1 and group 2, the group 1 will be the better reducing agent than the group 2 because they're all having the high standard electrode potential values. Here, they'll be having less, but both are all, both the elements, I mean, both the groups, group 1 and group 2, alkali metal and alkali earth metal, both are the very good reducing agents. For comparing, I'm saying the group 1 will be the better reducing agents. Reducing agents in the sense what happens, that should be ready to lose the electron. But here what happens in group 2, in balance there is 2 electron is present, right? So it is hard to remove the 1 electron from the 2 electron. In group 1, what happens, there is only 1 electron in the valence sheet. So it is easy for you to remove the valence electron. So that's why group 1 will be the better reducing agents than group 2. That's why the standard electrode reduction values has been mentioned here. These are all the experimental values. You don't need to worry. Only I'm insisting that group 1 will be having the high standard reduction potential values. Clear? Clear with this thing?
Yes, ma'am.
Okay. Now, ionization enthalpy. So if I'm speaking about the ionization enthalpy, here itself we have discussed the ionization enthalpy. Okay. So in this table itself we discussed. Now, I'm asking you the question. If I'm taking the first ionization enthalpy, okay, we can compare between alkali metals and alkaline earth metals. Okay. So which one will have more ionization enthalpy, whether it's alkali metals or alkaline earth metals?
Alkaline earth metals.
Why?
Because in alkali metals, there's only 1 electron in the outermost shell.
Exactly. Very
So
good.
it can
You're right.
easily lose the electron.
Exactly. So here in alkali metals, there is like 2, 8, 1. In first shell, there is 2 electron. In second shell, there is 8 electron. In third shell, there is only 1 electron. But in alkaline earth metals, there is 2, 8, 2, which means there is 2 electrons. Okay. If there is 2 members, it's hard for you to pull them. So similar thing follows here. So that's why alkali earth metal will be having the first ionization enthalpy more. Okay. Now, coming to second ionization enthalpy, what happens here?
The second ionization enthalpy of alkaline earth metals would be alkaline metals would be more than that of alkaline
Yeah,
earth metals.
exactly. After removing this electron and after there is only 1 electron here, this will becomes the stable configuration, right? Noble gas configuration. So to remove the electron from this stable configuration, it is hard and you need to absorb more energy. So the second, that's what insisting. The second ionization enthalpy of alkaline earth metals will be smaller. Okay, and the first ionization enthalpy of alkaline earth metals will be higher. Okay, that is what the thing insisting here. And the trend, what happens to the trend from beryllium to barium? It follows a decreasing trend, no exceptional case. Clear this, clear with this slide?
Yes, ma'am.
Okay, next one, hydration enthalpy. Similar concept, what I have already said in the previous alkali metals. So here in hydration enthalpy, you can see because of the ionic size, okay, if the ionic size decreases, the polarizing power increases. If the ionic sizes decreases, the electron density also will be more. So what happens, the interaction between the ion and the water molecule will be more. So beryllium will be, due to its small ionic size, this will be having the highest hydration in enthalpy. So barium will be having the lowest hydration enthalpy. So here, okay, you can see, you just don't need to, you can see the magnesium and calcium chlorides, no, they will be forming their respective hydrated salts like this. Okay, they'll undergo hydration like this. While this sodium and potassium, that is sodium chloride and potassium chloride, they do not form such hydrates. Why? Okay, so you compare the hydration energy of group 1 and group 2. So which group will be having the maximum hydration enthalpy?
Group
Hydration
2.
enthalpy, group 2. Very good, because it will be very much smaller in size, right? So due to the smaller in size, what happens? This sodium and potassium will be having the lesser hydration enthalpy. So that's why it can't form such hydrates. So lithium is the only possible element in the group 1 that can form the hydrated salts, whereas the sodium and potassium will not that much easily form. Whereas this magnesium and calcium, which belongs to group 2, they will have the larger hydration and enthalpy. So that's why they can easily form their respective hydrates. Clear?
Yes, ma'am.
Okay. Now, physical properties of alkaline earth metals. See, as your in group 1 itself, in alkali metals itself, we know they're all like a light, harder metals. So if you're comparing the group 1, so group 2 will be harder, but what happens? That is also light, little bit harder. Okay. So see, but harder than the alkali metals. Okay, because of the small size and small crystal lattice, what happened? It will be little bit harder than the alkali metals, and they're all like silvery white, lustrous, and relatively soft. And if you google the beryllium and magnesium salts, you can see they'll be a little bit grayish. Okay, don't need to come and see this point, melting and boiling point of these metals. Okay, group 1 and group 2, which group will be having the higher melting points? Obviously it will be group 2, right? Because they'll be very much smaller in size. So what happens? You need to give more heat to break the crystal lattice. So group 2 will be having the more melting point and boiling point. And see, as I already mentioned, the trend, okay, this is not systematic because of its low ionization enthalpies, which will follow the down the group, and is also the lattice arrangement is also not proper there. So, and they're all follows a strong electropositive. That is, the tendency to lose the electron is also good down the group, and the electropositive character also increases from beryllium to barium. So, clear with these points?
Yes, ma'am.
Okay. Next. Yeah, coming to this point, see, calcium and strontium and barium, the three elements can impact brick red, crimson, and apple green color. You know about the flame test, when you're just showing the flame, the salt in front of the flame, the valence electron that will be present in the ground state will move to the excited state, and while coming back to the ground state, it releases the electromagnetic radiation that will be in the form of visible light, so that you will be getting this brick red, crimson red, and apple green. But only calcium, strontium, and barium can impact colors. This beryllium and magnesium can't, because group 2 elements are still more smaller, right? If it is still more smaller, in the sense the nucleus won't allow the electron to jump from the ground state to excited state. They are too strongly bounded to the nucleus. So what happens? They can't jump to excited state. So there will be no flame test, and they can't impact any color because of the strong domination of the nucleus. This beryllium and magnesium will not impact color. Only calcium, strontium, and barium will be impacting color. Okay, and in flame test also, this calcium, strontium, barium, that will be actually in flame photometry they'll be useful in your 12th practicals or 11th practicals. You will do the salt analysis. Okay, so there with the color of the salt, with the color of the flame itself, you will easily identify this is calcium, this is strontium, this is barium. So in that particular thing, it is just useful. And finally, the high electrical and thermal conductivities will be more in alkali metals, not in alkaline earth metals. Why? Because alkali metals, okay, compared to alkaline earth metals, alkali metals is little bit larger. Okay, so what happens there? The free electrons will be more. Because of this free electrons, it can easily conduct electricity. See, alkaline earth metals also can conduct electricity. Comparatively, alkali metals will be quite large in size. So what happens? There will be free movement of electrons will be there. So that wise it show high electrical and thermal conductivities. Okay, so that's why many metals, in conductors, the alkaline alkali metals, they'll be preferred. Clear with this slide?
Ma'am,
Yes.
also we can say the conductivity of electricity increases down the group.
Conductivity, electricity. Yeah, exactly. Exactly, because down the group, you know, the shells is getting increased, right? The movement of the electrons will be like more vast. Okay. So what happens? They'll be automatically, obviously, they'll be getting increased down the group. Okay. The metallic nature is increasing in the sense what happens there? The conductivity will be getting increasing. Okay. Clear?
Yes, ma'am.
Okay. Next one is chemical properties. As we have discussed in last class about the alkali metals, now we are getting into the alkaline earth metals. Okay, so first, see, beryllium and magnesium, they're all kinetically inert. Actually, there we will be taking the lithium. It will easily react with oxygen and it will form monoxide. Sodium will form peroxide, and rest of the three oxides, that is potassium, rubidium, cesium, all the three elements will form their superoxides. I said this is based on their size. Okay, but here it's not like that. See, this beryllium and magnesium, what happens? Being a metal, all our metals, what happens? When it is exposed to air, it will react with oxygen. It will form a thin oxide film, which means, say for example, if this is a beryllium metal, okay, so what happens here? There will be thin oxide film will be formed on the surface of the metal. So after that, there will be no reactivity. Okay, this is with the presence of oxygen. So there will be no reaction after that. So what happens? They won't take this beryllium and magnesium as a metal. Okay, because what happens once if you're taking it as a metal, it will form this oxide film and there'll be no further reactions we can carry over. So they will be taking this beryllium and magnesium in a powdered form. Okay, so why we are taking it in a powdered form? To make the reactions. So if we are taking this beryllium and magnesium in a powdered form, there we can treat it with oxygen and nitrogen. We can obtain this respective oxides and nitrates. I'll write the reaction. Wait. I'll be writing here itself. So if you're just taking the beryllium, okay, with oxygen, it will easily forms the beryllium oxide, which means 2. Okay, and if you're just taking this beryllium with nitrogen, nitrogen will be having 3, so it will be like this. It will be like B3N2. Okay, so this beryllium oxide and beryllium nitrate, no, by this reactions only this product will be obtained. Do remember this beryllium is in powdered form. This is in amorphous form. Okay, so by this only the two products will be obtained. Similar thing will also obtain it for magnesium oxide and magnesium nitrate. So the similar reactions, you can replace Mg here and you can carry over the reactions. Finally, your product will be obtained. The only reason is because of the presence of the oxide film as in metallic form. Now, in calcium, strontium, and barium, there is no such barrier. Okay, as a metal itself, you can easily react it with the air and they'll form their respective oxide and nitrate. So I'll write the reaction here. Yes. So the reactions like you can anything like metal oxides and metal nitrates. It will be like this. You can replace it as M as any metal like calcium, strontium, and barium. And also with water, they'll form their respective hydrogen. Sorry.
Oh, it should be M3N2, right?
Yeah. Sorry. Yes. Nitrogen 3 M2. Yes. So they'll be forming the respective oxides and nitrates. Okay, so this is what the thing you have to remember. Only one point. The thing is actually this beryllium and magnesium as a metal, it won't react directly with oxygen and nitrogen because of the presence of the oxide film on its surface. But in amorphous form, that is in powdered form, what happened? It will react with oxygen and nitrogen. They'll form their respective oxides and nitrates. But the rest of the metals, as such as a metal, it will react with oxygen and nitrogen and they form their respective oxides and nitrates. And one more thing is, see there, lithium will forms monoxide and sodium will forms peroxide. All these kinds of discriminations is there. But here it's not like that because of the sizes. Okay, you can ask me down the group, there is more number of sizes, but the thing is, Here they don't tend to form monoxide, peroxide and superoxide. Okay, they'll only form monoxides. All the elements will be forming monoxides, and at very rare conditions only, this strontium and barium will form peroxide. Only at rare conditions, and that is also not in your syllabus. So just don't complicate it. This is fine. Okay. So understood with this
Ma'am,
slide?
I have a doubt.
Yeah.
And then what about the rate of reactions down the road?
Rate of the reaction actually down the group. You're asking about this oxides or nitrates or general rate of reactions for the elements.
Oxides and nitrates.
Oxides and nitrates, what happens? It will shows an increasing trend only. Okay. Actually, down the group there will be increasing trend, but there will be what happens? The peroxide, superoxide will not be there. Okay, there will be slight increasing trend will be also followed. Okay.
Okay, ma'am.
Okay. Now, reactivity towards halogens. So here, with halogens, what happens? Every metals will react with halogens and forms their respective halides. Okay, so halides in the sense, see, this metal can be anything of like beryllium, magnesium, calcium, strontium, barium. And this X2 can be of like, you can take any halogen. Say, for example, if I'm taking beryllium, it can react with this halogen and it will forms this beryllium chloride. So make sure the point elevated temperature. What is elevated temperature in the sense? There is no fixed temperature. Okay. So you have to adjust the temperature at which point the temperature, the product is formed, you can take that point. And one more thing is this temperature will not be stable at every situations. Say for example, if the beryllium chloride at one time, if it is getting at 200 degrees Celsius means at another time it can obtain at 220 degrees Celsius. So that's why they have mentioned the term elevated temperatures forming their halides. Okay. And one more exceptional case is the beryllium, what happens in the sense, as such, it can't react. Okay. React with the chlorine and form beryllium chloride. Rest of the, if you're taking magnesium, it can react with chlorine and forms the magnesium chloride. But beryllium, what happens? It can't react directly as a beryllium metal. So what it will do, you can take the beryllium oxide, you can react it with halogen and you have to take the carbon and finally your beryllium chloride will be obtained. Okay, being very small, this is the problem to fix it. That's it. Okay, so this by this process only the chemical reaction undergoes to obtain this beryllium chloride. This reaction is directly not possible. Okay, so every reaction will undergo only at a fixed temperature is not possible. Elevated temperatures is possible. So that's why in halides they don't mention any kind of temperatures. Clear?
Yes, ma'am.
Okay. So make sure this reaction is not possible. Okay. I just considered after magnesium or calcium chloride, it will forms calcium chloride directly. But here you have to take the oxide treated with the halogen and carbon. Finally, your beryllium chloride will be obtained. Now, reactivity towards hydrogen. Okay. So similar thing. Actually, every metal, like all the metal, it will react with hydrogen and forms their respective hydrides. Anything like calcium hydride or magnesium hydride, anything. Hydrogen 1, calcium 2, yes. Magnesium hydride. So everything will be formed. But beryllium, what happens? It can't directly combine with hydrogen because beryllium is very much small. Hydrogen is also small. So what happens here in the sense? What happens? You have to take this beryllium halide. You have to treat it with lithium aluminium hydride. You all know the lithium aluminium hydride is the strongest reducing agent, right? So after treating it with lithium aluminium hydride, it forms the beryllium hydride. So from there, the lithium chloride, aluminum chloride, it will be getting reduced. So here only your beryllium hydride will be formed. Okay, but rest of hydrates. But rest of the elements, apart from beryllium, magnesium, calcium, strontium, barium, all the 4 elements can directly react with hydrogen and they form their respective hydrates. But in case of beryllium, you have to take the strongest reducing agent and you have to react it with beryllium halide, and finally a beryllium hydride will be obtained. Okay, so clear this reactivity towards hydrogen. So in alkali metals, what happened? All the elements will form their respective hydrates. Just compare the alkali metals and alkaline earth metals so that you will be not getting confused at any point of time. Clear? Clear, guys? Any doubt? I can't understand.
Ma'am,
Yeah.
ma'am, so alkaline earth metals will react easily with hydrogen compared to alkali metals.
Wait 1 minute. I think why there is only 4 members present here. What about the rest of the members? Is there any technical issue for them? What happened to the rest of the members? Only 4 is present. Yes, do you know what about the rest of the members?
I'm not sure, ma'am.
Not sure. Okay. Yeah, the one who raised the doubt, please ask here.
Ma'am, so alkali metals will react easily with hydrogen or alkaline earth metals?
Wait, someone texted me. Wait. Ma'am, can you please give me call after 11 class? Okay. So, is there any problem with the technical issues? What's wrong? Yeah, one more got connected. Shri Giridhar. Okay. Wait. Okay. Yeah. You're asking group 1 will be having the more reactivity towards hydrogen or group 2 will be having the more reactivity towards hydrogen. You are comparing that thing, right?
Yes, ma'am.
Actually, here coming to the point, group 1, that will be having the more reactivity, because what happens, there will be 1 free electrons, right? And also quite it is larger in size, right? So that will be having more reactivity, and group 2 will be having the less reactivity. Clear?
Ma'am, but group 2 has smaller size, right? So smaller size would easily react.
Smaller size is also one of the reason, man. The thing is actually, see, if there is an electron which is like free and it is ready to occupy, there only you can make the bonding, right?
Okay, ma'am. Understood, ma'am.
Yeah. Now, moving to reactivity towards acids. Okay, so reactivity towards acids. So here what happens, every alkaline earth metals that will react with this hydrogen that is nothing but your acid. You can take this hydrochloric acid, HCl is taken here, anything like H2SO4 or HNSO4, it will form their respective salts. Okay, if you're just taking see, if you're taking Mg, okay, when you're reacting with, it will form your magnesium chloride with the release of H2 gas, okay, which is nothing but your salts. Okay, so likewise, if you're just treating it with H2SO4, what happens? Their respective sulfates will be formed with the release of H2O. So all the metals will react with acids and they form their respective salts. Even bases, even when they are reacting with bases also, they will form their respective salts, okay? Because they are all alkaline in nature. So this reaction is nothing but when it is reacted with acid, it forms their respective salts with the liberation of this hydrogen gas. That is the reactivity towards acids, okay? Reactivity towards oxoacids is different from this reactivity towards acids, okay? So here, this is an oxoacid, fine. But we will compare the trend in the forthcoming slide. We are taking here as a simple acid like HCl, HNO3. Yes, of course, this is an oxoacid, okay? In forthcoming slide, you will also read about the trends which is followed in the oxoacids, okay? So don't need to complicate here. Shall I move to next slide?
Yes, ma'am.
Yeah. Next, as I already said about the reducing nature. Yes. So before 5 slides, I have already discussed about the standard reduction potential, which is nothing but the reducing nature. Okay. So standard reduction potential will be more for alkali metals when you're comparing only the values. Okay. So here means there it will be having the high negative values. In alkaline earth metals, there will be a less negative values. Okay. So here, what they have been said, this alkaline metals are all strongest reducing agents. Yes, we agree. But when you're comparing the alkali metal and alkaline earth metal, there what happens? This alkali metal will be the like strongest reducing agents because there is only one free electron. But in alkaline earth metals, there is two free electron. So that's why this alkali metal will be a better and a strong reducing agents than the alkaline earth metals because of the highest negative standard electrode reduction potentials. Okay, so that is what they have discussed here. And also they have brought the point, this reducing nature also we have discussed about the large hydration energy associated with the small size. Okay, but the hydration energy is also fine. You can ask me, ma'am, the hydration energy will be still smaller in case of beryllium. But why beryllium is not a better strong reducing agent in the sense? Reducing agents very important, and the foremost thing is they have to ready to lose the electron. Okay, then only they'll become a strong reducing agent. So that will be done by the lithium groups, right? So that's why the group 1 will be a better reducing agent than the group 2. That is what in the reducing nature they have been compared. Okay, I think that will be, this is what this slide talks about. Clear?
Ma'am,
Yes.
the reducing nature will increase down the group.
Reducing, yeah, exactly. It will increase down the group.
Okay, ma'am.
Now, this solutions in liquid ammonia. See, previously we have already studied about the solution in liquid ammonia. So there, you don't need to complicate like that stuff. The only thing is the similar thing will be happening here. But what happens? This is an alkaline earth metal, right? So what happens? This metal, it will releases the 2 electrons, and this 2 electron will go and join with ammonia. And what happens? It will forms the ammoniated electron, where that will absorb energy, and what happened? It will be getting released, and this will give the deep blue black solutions. Okay, so what happens? The ammonium ions will be formed, and here the formation of ions is not mentioned, and the formation of ion is less feasible here. Okay, sorry, formation of amide is less feasible here. So that's why they have not included here. Up to this reaction is fair enough. The only thing is like 2+ ions will be getting released from the metal, where the 2 ions will be go with the Y moles of ammonia, and they'll form the ammoniated electron, where the ammoniated ions will be getting there in the solutions. Okay, so this is the solutions in liquid ammonia. And next one is, I think there will be okay, this is the uses. So is there any doubt in this reaction? Yes or no?
Ma'am, the X and Y represents the number of electrons.
This is the X moles of ammonia and Y moles of ammonia. Okay. So actually, if you will take 1 mole of ammonia, 2 mole of ammonia, right? So this is only how much moles? Okay, it's not electrons. How much moles they are combining? We don't know how much moles exactly will be taking place in that solution. That's why we have been written it as X and Y moles. Okay.
Then what is the second part, the two electron NH3
Sorry, what is the second part in the sense?
The magnesium forms ions. Magnesium ions are formed, all right. But what about the second part?
Magnesium forms. What is magnesium here? Okay, you're saying about if the metal is a magnesium. Yeah.
Yes,
Hello.
I mean the metal forms ion, its respective
Yeah.
ion. But
Yeah, carry on.
what is the second thing, like two electrons NH3?
That electron only making this blue color solutions. That electron only giving this color. No. See, if it is in the beaker in the sense, okay, if this is a beaker in the sense, there will be like Mg plus 2 plus and 2 electron minus will be there, right? Okay, it will be there in the solution like this, right? In the liquid ammonia.
Yes, ma'am.
Yeah. So this 2 electrons, what happens? This magnesium will go, this is an NH3 liquid ammonia. This Mg2 plus will go and combine here, whereas this 2 electrons also will go and combine with this ammonia. When it is go and combining here, what happens is electron, what happens? It will absorb the energy and it will release. So that's why the solution color will be turning into the deep blue black solutions. Okay.
So the deep color is because of the ammoniated, the electrons attached to the ammonia.
Yeah, exactly.
All right, ma'am. Understood.
Yeah. And in the previous, in alkali metals, there is another one of the thing is also added, because what happens, first deep blue color solution will be obtained. And later on again, what happens, the bronze color will also obtain. What happens, there will be the remaining electrons will be there. No, again it will go on attack the metal. So finally there will be the color changing process will also take place. But here it stops till this only. So that's why deep blue black solutions only there, and there is no formation of amide. It is less feasible. So that's why they have been stopped till this thing. Okay. Yes. Uses of alkaline earth metals. So actually, I think these are all the things you can go by yourself itself, because being a users, but I'll still explain. See, beryllium, as I already said, it is very small. If it is very small, its crystal lattice also will be like tightly packed. So it is really the strongest metal. So if it is the hardest metal in the sense, what happens? It is used in big factories. You can see there is a spring. Okay, it will be like this, which this spring used to lift the big large amount of containers. So this rings are made up of beryllium. Okay, because of its crystal lattice is very strong. And in X-ray tube, have you watched in X-ray tube? I think you have been studying your 10th standard or 9th standard. There will be one tube. Okay, so the ignition should be present there. So to this tube will be made up of beryllium. In your Google, you can see in the X-ray tube there will be the ammonium. Sorry, it's not ammonium. The beryllium will be there. Wait, I'll draw it. It will be like this. So here this beryllium metal will be placed here. Okay. Why? In the sense to make it as very narrow and also to make the conductivity. Okay. So that's why the beryllium, metallic beryllium is placed there. And it forms alloys with the aluminum, zinc and magnesium. Okay. So as I already discussed, this aluminum and magnesium both will be used in the aircraft constructions. That is, the durability is very much higher because of the strong metal. So that's why they are all using in this aircraft construction. Even in your home, there will be a rice cooker. No, the base part of the rice cooker is made up of this magnesium and aluminum. Okay, so it can it will be highly resistant towards the heats. And this magnesium is used in the splash powder. It is also used in crackers also. Okay, it is a powder. When you just throw it, what happens? Immediately it will blast and bombard. So that is why it is used in flash powder, in bulbs, and in bombs. Okay. And do you know the milk of magnesia? So what is antacid? Antacid is present in our stomach. Okay, that will relieve the indigestion, and also if there is any kind of burps and hiccups is there, this antacid is making some kind of disturbance in its stomach. So this milk of magnesia, they'll be used immediately. If you're just drinking it, what happens? It will relieves it. So it is used as an antacid. And you know, there is a famous dialogue, the magnesium is present in the salt. Okay. And calcium, there is one chapter called Metallurgy. In metallurgy, what happens? All the metals will not be as such present as metals. It will be present as a ores and minerals. So when it is present as ores and minerals, you have to, get through many number of reactions like froth flotation process, hydraulic washing, all that kind of thing. Finally, the purification will be done. In that purification, this calcium is one of the major things that will actually take the oxides from the metal. Okay, if the iron is present as iron oxide in the sense, we will use this calcium as a reducing agent where it can easily, separate that oxygen oxide from that metal, and the purest metal can be obtained. And finally, in vacuum tubes, to completely take the air from the vacuum tubes, being a metal, they'll be highly reactive, right? So what happens? To take out all the air, this calcium and barium metals will be used. And this radium salts, they're all radioactive elements. And in cancer treatment, in chemotherapy or radiotherapy, to destroy the cells, cancer is nothing but the abnormal growth of cells, right? To remove a particular number of cells. So this radium salt is used in that radiotherapy. So you can go by your text itself, this uses of alkali metals. Okay. Animations don't need to watch. Fine. Now, oxides and hydroxides. Okay. So there, if students, there is any doubt till the previous slide.
No, ma'am.
No. Okay. Now, coming into the oxides and hydroxides, here, coming to the point, have you heard the word amphoteric in my first class? Go there. Okay, in my first demo class, I asked which element is amphoteric in nature. Okay, do you remember which element is highly amphoteric in nature? I have raised the question there. Everyone is saying magnesium,
yes, ma'am.
Yeah.
Ma'am, but how can element be amphoteric in nature? The oxide of the element should be.
Oxides and hydroxides will be amphoteric in nature. Fine, okay, no issues. So I've been asked, I've been asking that which element. Okay, so your thought that you thought you have been restricted by the element, so you doesn't think about the oxides and hydroxides. Fine, fair enough. Okay, so what is amphoteric?
They react both with acids and base to neutralize.
Okay, how you will say this beryllium is amphoteric, this zinc is amphoteric, copper amphoteric? How you will say this amphoteric? How you will know that will be reacting with acid and base?
Because in reaction with water, they will release H plus and OH minus ions.
Okay.
So if they release both H plus and OH minus ions, then they are amphoteric in nature.
Exactly. Actually, these are all experimentally, it will be carried out in laboratory, and finally the reactions that we are all studying. Okay. So what happens in beryllium oxides? So actually beryllium is covalent in nature. Yes, that's fine. We can agree because it can't completely transfer its electron. It can only share the electron. So what happens here in the sense, when it is burned with oxygen, it forms a monoxide, and that is covalent nature, I agree. But if it is when you're reacting with water or whatever it might be, okay, what happened? It will be reacting with both acid and as well as base. And in both the conditions also, it gives their respective products. Okay. But the rest of the members will not behave like that. So that's why this beryllium oxide or hydroxide, that is highly amphoteric in nature. While other elements, what happens? They'll be ionic. They'll transfer the electron. So that's why this beryllium is amphoteric. And another one more thing is all the elements apart from beryllium, down the group, magnesium, calcium, strontium, barium, they're all highly basic in nature. Okay, only beryllium, because of their alkaline nature, they'll be basic in nature. Only beryllium will be amphoteric in nature, and all the elements will form their oxides and hydroxides. There is no inhibition in that. Only thing is the beryllium will be like their oxides and hydroxides will be reacting with both acids and as well as base. That's why it's amphoteric in nature. And one more thing is, all the mono oxides, they'll all be forming only the mono oxides. There will no peroxides or superoxides will be formed here. Okay. So coming to the next point here. Okay, this is an introduction. Here, just listen. See, the solubility, the thermal stability, and the basic character. Okay, all the three terms, what happens, increases with increasing in atomic number. That means, see, this beryllium, and just leave the beryllium because beryllium is amphoteric, so we don't incorporate beryllium here. Now we have to take only the magnesium hydroxide. So magnesium, calcium, strontium, and barium. Okay, all the four hydroxides, okay, alkaline earth metal hydroxides, they shows their solubility, thermal stability, basic character, everything is showing an increasing trend. What's the reason? This is a reaction of beryllium that reacts with base and it gives a product, that is beryllium hydroxide. Okay, and this beryllium reacts with acid and it forms, this is a coordination complex. Okay, tetra aqua beryllium 2 chloride. Okay, this is a coordination complex. So this is an example of how beryllium reacts with acid as well as base. Okay, now give the answer for my question. I have asked why it is showing an increasing trend for all the three categories: solubility, thermal stability, basic character. I have already disclosed. Just think about
due to the increase of the size.
due to the increase of the size. Due to the increase of the size, okay. Fine. But there is another one concept behind it. What about the rest of the members? I think you're the one who is constantly answering. Rest of the persons, I don't know why. I don't know who first. What is your name? Kanishk is not answering. Sri Giridhar is not answering. You're all simply listening. Huh? Okay. Due to the increase, you are saying due to the size. Okay, fine. Increasing size. Oh man, you're seeing this answer. You're seeing this thing and answering.
No, ma'am, due to the increase in size, the ionization energy would decrease. That's why.
Okay, the simple thing is, see, down the group, what happens? See, this OH is a big anion, right? So what happens? Barium is a big cation. That is nothing but the larger cation can stabilize the larger anion. That's why what happens? It will be getting stable down the group. The stability will be increases. That will be falling for the solubility and basic character. So the simple thing is like only the smaller cation, smaller anion that can goes within well. Larger goes well. Parallelly, you can't take the smaller and the larger one. That's why the solubility, thermal stability, and the basic characters of all magnesium to barium, it shows an increasing trend. Okay, and this reactions is how this beryllium is reacting with acid as well as base, and these are all the products. Okay, so any doubt, and make sure to know, and definitely in your academics point of view or any competitive point of view, definitely this trend they'll be asking anywhere. So they'll always omit beryllium because beryllium is amphoteric, they don't include. So out of, if you're just leaving the beryllium, the rest of the three is very, very important. Okay. So the solubility, it will be only following the increasing trend. Clear?
Yes,
Clear,
ma'am.
guys? Okay.
Yes, ma'am.
Yes. This S block, no, actually it's really the boring subject. But still you have to study. In inorganic, S block, P block, even D block is quite interesting. This S block is full of reactions, and the same simple concept will be followed everywhere. Now, except, okay, fine. Now we are taking about the halides. Okay, so as yesterday itself we have discussed, if you're just taking the halides in lithium itself, we have already studied. If you're just taking the lithium halide, it will be covalent in nature because it can't completely share, completely transfer. It can only share. So similarly, the beryllium also follows the same. So this beryllium halide will become the covalent one. And finally, what happened? It will solubilize in the organic solvents. This is nothing but a chloro bridge structure. Okay. So this chloro-bridge structure is nothing but how this beryllium chloride, generally it will be present as a linear monomer. Okay, this is a chain-like structure. It will be keep on going. Okay, and this chloro-bridge structure will be always formed for beryllium. And this beryllium is an electron deficient molecule too. This is a loose acid, right? You know the loose acid and everything. Loose acid and loose base. Loose acid in the sense electron acceptors, because there is only the octet electron can't be filled. Okay, so if the octet electron is not filled, they are all known as loose acid because they are in need of electrons. Okay, so when forming this bridge, what happens? All the 8 electrons will be surrounded here. So what happens? This octet configuration will be filled. I think you know the loose acid and loose base concept, right?
Yes.
Okay. Now moving to the next one. Yeah, exactly. This is the thing. So as this is nothing but as already explained now. See, the tendency to form halide hydrates gradually decreases, which means, see here you can see magnesium, calcium, strontium, barium. You can see the hydrated salts, it will be getting decreased. Why? The similar point, hydration energy, what happens to the elements, which means that will be decreasing trend from beryllium to barium. Similar thing follows here. Here beryllium, we are not taking beryllium chloride because it will be covalent in nature. So we are talking about the magnesium till barium. It will be showing the decreasing character because the hydration energy is showing the decreasing trend from top to bottom. That makes this halide hydrates also making decreasing down the group. So clear this point.
Yes, ma'am.
Okay.
Yes,
So
ma'am.
yes, if it is following a decreasing trend, what happens? See, these are all the hydrates which will be attached. Okay, so this will be very weakly attached. So just the heating is enough to break this molecule. That is what said. See, the dehydration of the bromide, iodide, of this calcium, strontium, magnesium, just a simple heat is enough to break because it's a weak attachment, right? Okay, the interaction between the iron and the water molecule will be very, very weak. So just the heating is enough to break it. Okay, and you can see the fluorides is less soluble than chlorides because of their high lattice energies, because they are closely and tightly packed. So what happens there? It is not easily to solubilize. Okay, so that's why the fluorines are relatively less soluble than chlorides, moving to a high lattice energy. You can ask me, ma'am, if you actually no, I don't want to confuse. So you got this thing right? You got this thing. Any doubt?
Ma'am, could you repeat why fluorides are less soluble than chlorides?
Because of their lattice energies. See, what happens? It will be very closely attached, right? Okay. So if you need to break this lattice, what happens in chlorides? What happened? Quite, it will be, the lattice will be like this, right? Okay. So what happens to break this? You have to give, because of the high lattice energy, what happens when you're dropping it in a solution, it will not easily break it into the ions, right? When you're dropping in the solution, what happens? It will not solubilize that easily because the breaking of this closely arranged crystal lattice is tough, right? So that's why they are less soluble than chlorides. Clear?
Understood, ma'am.
Yeah. So actually, lattice in the sense the arrangement of electrons like this. Actually, they'll be doing like this, but you can see it as in a crystal form also. It will be like this. You can go through the Google in the images and everything. You can see the crystal lattice picture. Yes. Now salts of oxide. There also you studied salts, and here also you're studying. Yes, first one is carbonates. So here in carbonates, you can see there, yes, one question. We have already studied about the trends of the carbonates in alkali metals. Do you remember? From lithium carbonate to cesium carbonate, I said about the solubility as well as the stability. What happens there?
stability increases.
Yeah, solubility is also getting increased down the group, because this lithium carbonate, what happens, just if you're just slowly, just a slight heat is enough to decompose the lithium oxide and carbon dioxide, easily decompose. Okay, so what happens there, the trends will follow an increasing trend from lithium to cesium. Here what happens, the solubility decreases. Okay, why decreases in the sense, because you can't take the carbonates as well as, like, you can't take the carbonates if you're taking like beryllium carbonate or magnesium carbonate directly, you can't make it into insoluble in water. You need to precipitate it by adding the sodium and ammonium carbonate solution. Okay, so then only it shows the solubility. Okay, so as such it won't show the solubility. So while adding this precipitate of sodium and ammonium carbonate, there it will show the solubility. That solubility also very, very less. Okay, so completely all the carbonates will not completely solubilize. Partially it will get solubilized. The reason, that is why the solubility of carbonates in water decreases as the atomic number of the metal ion increases. There the trend is different, here the trend is different. Okay, because the reason is, comparatively the ions are very much smaller, so that's why additionally we are adding this precipitate to make it easy to solubilize in the solution. And finally what happens, partially it will get solubilized. If you go through the Google, if you just go through the beryllium carbonate solubility, there'll be images where half of the solution, the beryllium getting dissolved, and down the beaker, what happens, there will be some particles will be remaining there. Okay, so less solubility, and down the group also the solubility will be getting decreased. And what happens, see, all the carbonates decompose on heating to give carbon dioxide. So here what happens, there only lithium will be decomposed, but here everything will be decomposed to give the their respective oxides and carbon dioxides. Okay, so here what happened, all the carbonates decompose on heating to give carbon dioxide. So this beryllium carbonate is also unstable. Like lithium carbonate, here the beryllium carbonate is also unstable, and down the group what happens, the stability will be getting increased. This is only of stability, this is solubility. So what happens, beryllium, magnesium, calcium, strontium, barium, in the sense, if you're taking barium carbonate, so what happens here, so here this is a bigger anion, this is a bigger cation, so it will easily getting stabilized. So what happens, the stability will be getting increased. But in terms of solubility, what happens, you have to precipitate it with the sodium and ammonium carbonate. Okay, clear?
Yes, ma'am.
Next, sulfate. So in sulfates, what happened? They're all actually this beryllium sulfate, magnesium sulfate, calcium, strontium, barium are all will be like white solids. Okay, they're all stable to heat also. So here, this beryllium and magnesium will be readily solubilized in water. So what happens here in the sense, this beryllium, magnesium, no, they'll take the hydration enthalpy as a dominating factor. Okay, because this beryllium and magnesium, they're all smaller cation. This is a bigger anion. So what happens? It will not be fixed that closely. So when you are like putting into the water, what happens? Easily it will take the advantage of the hydration energy and easily they'll get solubilized. But coming to calcium, strontium, and barium, these are all quite a bigger cation. This is a bigger anion. These are all quite a bigger cation. This is a bigger anion. So what happens? They'll fix it. And the solubility will shows a decreasing trend from calcium to barium. And in beryllium and magnesium, what happens? Due to the instability of the smaller cation and bigger anion, the hydration energy will take the dominating factor and easily they'll be getting dissolved. Clear about the sulfates?
Ma'am, so solubility increases down the group.
No. If you are just taking for solubility, they won't include beryllium and magnesium. Only they'll be saying from calcium to barium, the solubility decreases, which means it will be like this: calcium sulfate, calcium, strontium, and barium. It will be like this. I'm saying in competitive level, they'll be the question will be raised because they both will be getting solubilized, right? So we don't need to include. So the pattern will be only for these three comparisons. Clear?
Okay, ma'am.
Okay. Because they both will be getting solubilized. Okay, because of its hydration energy, they both will be getting solubilized. Just look at here, the greater hydration enthalpy of beryllium and magnesium overcome the lattice enthalpy factor. Why it is overcoming? Because the instability. This is a smaller cation. This is a bigger anion. So that's why what happened, their hydration enthalpy will take the advantage and they'll be easily getting solubilized. Shall we move to the next slide?
Yes, ma'am.
Okay. Now nitrates. So here in nitrates, what happened? There is a reaction. So easily we can't take the nitrates directly. We can't, directly we can't obtain the nitrates, which means we will take the carbonates. The carbonates in the sense the respective metal carbonate, any alkaline earth metal carbonate. So just write it like this: any alkaline earth metal carbonate. This will be treated with dilute nitric acid. Okay. So what happens here? This metal will react with this nitric acid, that is with this NO3, and it will form their respective nitrates. Okay, it will be like this. And see which balance means the 2H2 gas water molecule should be there. So H2O water and your carbon dioxide will be released. Okay, so this is the formation of the alkaline metal nitrates. Okay, so to obtain this alkaline metal nitrates, you have to take the alkaline metal carbonates should be treated with HNO3, and finally your alkaline metal nitrates will be formed. Okay, so this is clear. Now coming to the second point, what happens in the sense, this again shows a decreasing trend. See, all the alkaline metal nitrates can be formed. There is no exceptions here. So out of this, if you're taking beryllium nitrate, magnesium nitrate, calcium nitrate, strontium nitrate, barium nitrate, what is the trend follows there in the sense? See, again shows a decreasing tendency, okay, to form hydrates with the increasing and the decreasing size of, actually the trend will be following is a decreasing trend. Okay, why it is following the decreasing trend in the sense? Because of its hydration enthalpy. Okay, for beryllium, it will be having more hydration enthalpy. So if you are just taking this beryllium nitrate, this will be having the more solubility. Okay, if you are just taking this barium nitrate, due to its higher hydration enthalpy, it will be showing less solubility. So what happens? Again shows a decreasing trend to form hydrates in the sense, when you're just dissolving into the water, definitely there will be a formation of the hydrated salts will be there. So the hydrated salts will be of, if I'm taking MgNO3.26H2O, this is the hydrated salts. Okay. And down the group, what happens? If I'm taking for barium, what happens? It will be like this. In barium, what happens? There will be no attachment of water molecule will be there. It will as such remain as an anhydrous salt. So I'm saying only about the hydrates, formation of hydrates, the trend will be following a decreasing trend. Clear with this point? So first thing is, I said about the preparation of the alkali metal nitrates. Okay. So the preparation is done by, you have to take the metal carbonate, alkali metal carbonate, you have to treat it with HNO3, and your alkali metal nitrates will be formed. Again, you're introducing into the water. Okay, when you're dissolving into the water, what happens to the hydration enthalpy? So the hydrated salts formation will be less when you're getting down the group, because of the fact, the trend which is already following, the hydration energy will be getting down the group decreased. So the attachment of water molecule down the group is less possible. Okay, as you already know, the electron density will be less when you are just increasing the size of molecule. That is what the trend which have been discussed here. Clear?
Yes, ma'am.
Okay. Next, anomalous properties of beryllium. So similarly, we have already discussed about the anomalous properties of lithium, right? The similar pattern follows here. The first one is beryllium as such, these are all the stories, the similar thing, because of the exceptionally small atomic and ionic sizes. Okay, first one. Second one is due to its high ionization enthalpy, and rest of all the members are ionic, and only beryllium is acts as a covalent compound. That is the first reason. And Second one is, what is the coordination number? What is coordination number? Have you came across the chapter coordination compounds? Central metal atom, ligand, there will be a formation of complex. Have you came across the chapter? Is this the 11th chapter or 12th chapter? Coordination compounds. Yes, come on, answer
No,
me.
ma'am. Could you explain?
Okay, nothing. See, coordination number which is more than 4 in the sense, if I don't want to get into detail because there you'll be extra there, if you're just getting into the chapter, it will be like you'll be discussing it elaborately. But for here I can explain. See, beryllium will be having 1s2, 2s2, but there is an empty 2p shell is there. Okay, here, see, this is a nucleus. The first shell has 1s, the second shell has 2s and 2p, which means the 2p is filled. It is having the empty 2p. 2s is filled, empty 2p. So, this is 1s2, 2s2, and 2p will be like this, which means there will be one, in excited state, what happens? This one electron will goes here, and maximum of, there is only 1, 2, 3, 4. The 4 orbitals are there. Only the 4 electrons can be participated in that. Okay. There is, because there is no d orbital is present in it. Right. So the coordination number will be maximum of 4 is only possible. But for magnesium, what happens? There will be 1s, 2s, 2p, 3s, 3p, and 3d will also be there. Can you get my point? Can you
Yes,
get my
ma'am.
point? Yeah. So there, the maximum coordination number will be 6. Actually, for a complex, there will be only the 6 coordination number will be there, because there will be only 6 ligands will be attached to the central metal atom. If I'm getting into that, it will be getting prolonged. So just know this point. The beryllium is only can exhibit the coordination number 4. The rest of all the members can show 6, because rest of all the elements will be having their d orbitals. But beryllium is not having the d orbitals. It is only having the s and p orbitals with it. So that's why the beryllium does not exhibit the coordination number more than 4. Okay. Now, the oxides and hydroxides of beryllium, of course, it's completely different, because they're highly amphoteric in nature. They can react with both acid and base. Okay. But rest of the thing were all only basic in nature. So that is also one of the anomalous properties exhibited by the beryllium. So only 4 point you just note to clearly know. One is the small size. Second one is the high ionization enthalpy. Third one is due to the covalent character. Fourth one is the coordination number will be 4. And fifth one is they are amphoteric in nature. So that is the anomalous properties. Clear, guys?
Yes, ma'am.
Okay. Now, diagonal relationship. Already we have discussed this thing. Okay. So this beryllium, okay, group 2 beryllium will show a diagonal relationship with group 13. Here boron, here there will be aluminium. Okay, it shows a diagonal relationship with aluminium. So first reason is, see, if you're taking the ionic radius of beryllium is 31 in the sense, it will be nearly, aluminium will be of around, I think aluminium will be of around 28 or 29. Okay, exactly, I don't know, 28 or 29. So nearly the ionic radius is coming under the similar thing. And this beryllium also shows a charge by radius ratio, that metallic character also in a similar thing. First one, this actually the beryllium and magnesium, what happens, being a metal, when it is exposed to air, they form the oxide film. This aluminum will also form the oxide film surface. Okay, that is one of the similarity. Second one is, only this beryllium and aluminate can exhibit in the ionic forms. This is nothing but an tetrahedral complexes. It will be like this, BOH4 like this. Okay. So it will be like this. This can be exhibited as berylate ion. This can be exhibited as aluminate ion. Okay. And both can form the chloro-bridge structures. Chloro-bridge structures in the sense, see, aluminium, it will be having 3 plus as the valence electron, right? Cl, 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 and one of the Cl, you know, it will be connected like this. Okay. And third, and another one, it will be connected like this. You will be studying all this thing detailedly in your pre-block elements. It will like keep on, it will be going. So whereas this beryllium will also can form the chloro-bridge structure. Okay. Because why it is forming chloro-bridge structure in the sense, both are Lewis acids. See, aluminium, it just has only 6 electrons. Okay. So if it is having only 6 electrons in the sense, it can't complete its octet. Okay. So what happened? It is an electron pair acceptor. Someone should come and donate the electron so that it can fill the octet configuration. So say for example, if aluminium like this, AlCl3 in the sense, so there is, here, in order to fill the octet configuration, this ammonia, no, it will be like this. In chemical bonding, you knew about all these kinds of things. So this lone pair will come and attach here. Okay, so what happened? It will be like Al, Cl, 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 and what happens? This nitrogen will be like this. So now what happens? It will become an octet configuration. 1, 2, 3, 4, 5, 6, 7, 8. So what happens here? It octet is filled. So both are all Lewis acids in the sense they are electron deficient molecules in nature. So that's why what happened? They are ready to accept the electrons from any neighboring molecule or atom. And finally, this beryllium and aluminium ion, they'll actually in coordination complexes, you can see this beryllium and aluminium will form most of the complexes. Okay. Of course, there is like iron also will form most of the complexes, but these two will have the tendency to form the complexes. So that's why this beryllium and aluminium is showing the similarities. Okay. Clear with this thing? Shall we move to the next slide?
Yes, ma'am.
Okay. Next, compounds of calcium. Okay, so here we have, I have included only 1, 2, 3, 4, and after this thing, I think your S block element is over. Yes. So first one, calcium oxide or quicklime. I don't know how many persons know Tamil. In Tamil, it's known as sunambu. Okay, which is nothing but the limestone, general limestone. Okay. So what happens? You can produce this limestone just taking this calcium carbonate. Okay, if you're just taking this calcium carbonate on heating, what happens? It will easily dissociate into calcium oxide and carbon dioxide. Okay, so this is known as quicklime. So actually it's an amorphous solid. It's a very powdery solid. This is a melting point. And what happens? If you just exposed in air, what happens? It will absorb some moisture in the sense, still it will absorb moisture, it won't become moistury. Okay, it won't become watery. So, and it will absorb the carbon dioxide gas also. There will be tiny pores will be there in that stone. If the stone will be like, you can go and Google it, the quicklime also. It will be like a stones like this. Okay. So there will be another process called slaked lime. Slaked lime in the sense they'll add the water to it. You know, in building construction and all, they'll use that white cement. That white cement is nothing but the quicklime. Okay. So next one is, see, if you're just properties, if you're taking this calcium oxide, when it is dissolved in water, it will easily forms this calcium hydroxide. Okay. So what happens here? This calcium hydroxide is formed. No, this calcium hydroxide is known as the lime water or slaked lime. So this calcium oxide, when it is reacted with carbon dioxide, it forms the calcium carbonate. You can ask me, ma'am, if I place a calcium oxide, so when it is reacted with the atmosphere carbon dioxide, yes, of course, there will be the formation of calcium carbonate. Both will be looking similar only. Okay, right. What happens? So after when it is exposed to carbon dioxide, what happens? There will be a tiny pores will be there around this calcium oxide. Okay. So for the experimental reactions in laboratory, they'll be kept in a vacuum temperature. And what happens there? It will be a pure calcium oxide will be there. But whenever in building construction, when they open this calcium oxide from the box, immediately you can see the air bubbles will be there. Okay, so it will be easily reacting and it will form the calcium carbonate. And after once it is applied to the places around the walls, it will be become very thick and it will be getting hardened also. Okay, so that is nothing but your calcium oxide. And you see, the addition of limited amount of water breaks the lump of time, in the sense it will be like this big particles. So when you are just adding the water, what happened, you need to break the lump and you need to mix it and mix it and mix it. If you just go through the pictures, you can see it. That is known as slaking of time. Okay, and what happens finally, quicklime is soda is nothing but NaOH. Okay, so if you're just taking this calcium oxide, when you are mixed with soda, it will form the soda lime is nothing but CaHO NaO2. Okay, this is soda lime. Actually, this is used in the building material for many purifying agents also it is used. Okay, and taking this calcium oxide, when you're treating it with the silicon dioxide, what happens, it forms the neutral oxide. So what is this thing? Calcium oxide is acidic oxide or basic oxide?
Basic.
Basic oxide. Okay, this is a basic oxide. Metal will always tends to give the basic oxide. Silicon, it's a non-metal, it will tend to give the acidic oxide. So both acid and base reacts and it will forms a neutral oxide, which is also known as slag. Slag in your metallurgy. Okay. Similarly, again, if you're taking this basic oxide, treating it with acidic oxide, it forms calcium carbonate. Again, this is also one of the neutral oxide. It is one of the properties where this is used in the metallurgy, in the extraction. Okay, it is used as a slag. Why it is used as a slag? In the sense to remove the unwanted impurities which is happening in that reaction. So this is of calcium oxide. Okay, so just remember the first reaction, simple heat is enough to dissociate it, and the properties, what happens when it is reacted with water, what happens when it is reacting with carbon dioxide, and finally treating it with the acidic oxides, it forms a neutral oxide slag. That's it. Clear?
Yes, ma'am.
This preparations and all, it will be like quite boring only. So in manufacture of cement, see, yeah, this is the thing, this is the example. See, it will be like this only. After adding water, what happens? See, once if you're after adding water, the so many bubbles will be keep on coming, which means the carbon dioxide is getting evaluated. Okay, so that process is known as slaking of lime. So it is the cheapest form of alkali, and it is used in a actually in sodium carbonate. This is one of the major components, okay, in the preparation of sodium carbonate. And the sugar initially, once from the sugar cane you will take the sugar, it will be only in brown color. Okay, but the sugar which we are using in our home is white color. Okay, this sodium, this calcium oxide is used to bleach it. Okay, after bleaching only what happens, it will become white color. Okay, so that's why everywhere it's saying white sugar is hazardous. Don't use white sugar, in the sense there is only the components of this calcium oxide will be there in it. In also in dye stuffs, okay, it is used. Next one is lakered lime. That is nothing but your calcium hydroxide. There itself you studied calcium, taking the calcium oxide with water, your calcium hydroxide is formed. Okay, so that's what the thing. And what happens in the sense, aqueous solution is known as lime water, in the sense you have to take the quicklime, which is when it is mixed with water, there will be lime of water, in the sense it will be very much white color. So that is known as lime water. And finally, staked lime, in the sense you have to if you Google the pictures, you can see they'll be using one big rod. Okay, with that big rod they used to stir it. When you're stirring it, you can see it will be like it will be like a milk of lime, in the sense it will be white semi-solid paste will be present. Okay, so that process is known as lakered lime. To break the quicklime, add the water and again mix it, the semi-solid paste, that is known as this calcium hydroxide. Okay, so again, coming to the properties, this calcium hydroxide, when it is treated with carbon dioxide, it forms the calcium carbonate. When it is exposed to air, it easily forms the calcium carbonate. Again, taking this calcium carbonate, when it is treated with water and CO2, this is nothing but bleaching powder. Okay, sorry, this is calcium. Sorry, wait. This is calcium bicarbonate. Okay, sorry, hypochlorite is bleaching chloride. Sorry. So this is calcium bicarbonate. So excess of a hydrogen will come and sit here. Okay, and the next stage, what happens if you're just taking this calcium hydroxide with an halogen? What happens automatically? Calcium chloride will be getting released, and this calcium oxychloride is nothing but your bleaching powder. That is calcium hypochlorite is formed with the release of water molecule. So to prepare the bleaching powder, this calcium hydroxide, that is slated lime, is a major component. Okay. So in our day-to-day life, we are using this bleaching powder to clean, to clean the fungus when the walking surface is slippery. In the sense, we used to keep this we used to wash it via this baking powder, because it will use to remove all the germs and also the insects. So that's why we will be using this bleaching powder. It is highly reactive. Okay, it will be having that kind of pungent smell also when you're just inhaling. Yes, that is for calcium hydroxide. So simply just take the quicklime, combine it with water, it forms your calcium hydroxide. Coming to the properties, when it is reacted with carbon dioxide, it forms calcium carbonate. Again, taking that carbon dioxide, when it is reacted with excess of carbon dioxide, what happens? It forms calcium bicarbonate. Finally, the last property is, in the preparation of bleaching powder, we have to take this lacquered lime with the halogen. Finally, our bleaching powder will be obtained. That is nothing but your calcium hypochlorite. And finally, the uses is nothing but, what is mortar in the sense? Actually, it will be a binding agent. Okay, binding agent in the sense, while making in a building material, we will put sugar. Sorry, not sugar. Sorry, we will put cement, water, and of course there is something, a small stones, that is known as, like, I don't know the exact name of that. We will add everything, we will mix, and finally what happened, we will make that paste, the cement paste and everything. So we will also add this calcium hydroxide. Actually, most of the construction in these days, they are not adding, because it is already mixed in the cement itself. Okay, so it acts as a very good binding agent, so that what happen, it will mix everything, so that only we can make it the paste to build the construction. Okay, the cement paste. And next one, it is used in whitewash. Now only the emulsion paint and the Asian, Nippon, everything has came. But 2 decades back, they only use this calcium hydroxide, because what happened, it will destroy all the nano creatures and all the kind of small germs that is present on the wall. In the colder season, definitely there'll be the fungus will be present on the wall. So that only what happens after end what is after the December, no, after in the mid of January, what happened, again we will do the whitewash, because all the germs and the fungus will be present on the wall. No, we will use this calcium hydroxide to paint the wall, so that every germs will be getting killed. So that's why it is used in the whitewash. And in glass making, tanning industry, and yes, in preparation of bleaching powder, and in purification of sugar, white sugar. Okay, so these are all the things this calcium hydroxide is used. So any doubt in this?
No, ma'am.
Okay, I know this will be going only boring. Okay, fine. Next one is calcium carbonate. Okay, so I think there is only we can end up this class with calcium carbonate, and next is next class. I think half an hour is enough to complete the portions, and we will discuss some questions. Okay, I'll bring questions. So today, I think calcium carbonate I can complete. So if you're just taking calcium carbonate, it is nothing but actually your chalk piece. I know right now we have been digitalized. We are using the board and marker. While I'm studying, only the chalk piece is the only way to deliver the lectures for writing. So it is nothing but the calcium carbonate. Okay, so it is nothing but the limestone. See, chalk, marble, everything. So this can be prepared by using the slaked lime. Slaked lime is nothing but the calcium hydroxide. When it is treated with the atmospheric carbon dioxide, it forms this calcium carbonate. This is one method. Another method is you can take this calcium chloride, which is a salt. When it is treated with the sodium carbonate, it forms the calcium carbonate with the release of sodium chloride. So there are two steps to prepare this calcium carbonate. One is with slacked lime, another one is with calcium chloride. And while adding this calcium carbonate, while adding this carbon dioxide, we should be very careful, because if you are adding excess of carbon dioxide, this product leads to calcium hydrogen carbonate. Okay, so that's why what happened, we should be very careful while dropping this carbon dioxide in this reaction, first reaction. And second one is the properties. So if you're taking calcium carbonate, if you are heating, our quick climb CaO will be obtained, okay, with the release of carbon dioxide molecule. And next one is it will be reacting with the dilute acids, that is with HCl, with H2SO4, even with actually dilute means if we can also take HNO3, anything, it will form like calcium chloride, calcium sulfate, calcium nitrate, anything will be formed. They're all nothing but the salts. Okay, so with acid, it forms the respective salts with the release of water and carbon dioxide. This is also one of the properties. And next one is their, kind of use. So usage in the sense, first one, as I already said, in building materials, the calcium carbonate occupies a major role. And, what is flux? Flux is nothing but the purifying agent. Okay, purifying agent in the sense, again, in metallurgy, certain compounds, certain ores and minerals, they'll be having a maximum amount of impurity. Okay, so there this calcium carbonate will be adding as a flux. So what happens? It will reduce the impurity, not completely to take away the impurity. It will reduce the impurity. So that's why this calcium carbonate is acts as a flux, especially in the extraction of iron metal. It is used. Okay, so in high quality paper, you can see the white sheets, everything, you will use the calcium carbonate. And finally, as antacids. Okay, in antacids, if there is something is wrong, the calcium carbonate can also be intaken to relieve the digestion, okay, problems. And in dental industries also, they'll use the calcium carbonate to fix some tooths, okay. And finally, in chewing gum and filler in cosmetics. So in this way, the calcium carbonate is used in various industries. So just go through the preparations, just the carbon dioxide, okay, and calcium hydroxide and calcium chloride and sodium carbonate. These are all the reactants so that our calcium carbonate will be formed. And next slide is the properties, how it is reacting with the dilute property. Dilute acid, they'll give the respective salts. And what happens when we are heating. And finally, uses. So any doubt in this?
No, ma'am.
Okay. So I think we can end up the class till now. Even I'm really fed up. So there is only cement, of course. There is only 6 to 7 slides. So in the next class, I think probably 15 to 20 minutes is enough to S block elements. So any doubts in today's session? If you're quite hesitant or reluctant, please drop the message in my WhatsApp number. I'll definitely answer it. Okay. So today's class, if there is any doubt, please ask me. Or you can drop the message. I'm also looking in the message box also. No doubts. That's it. Clear with every concepts. Seriously? Hey, come on, guys. Yes or no? What's your answer?
No doubts, ma'am.
No doubts. Okay. So I'll bring the questions in my following class. At that time, definitely I will come to know whether like how you have really listened here. Okay. Yes. So thank you for attending the session. Thank you so much. We can wind up the session. Thank you.
Thank you, ma'am.
Thank you.